Finding equations of exponential functions. In the previous examples, we were able to write equations for exponential functions since we knew the initial quantity and the growth rate. If we do not know the growth rate, but instead know only some input and output pairs of values, we can still construct an exponential function. Example 5. In 2009, 80 deer were reintroduced into a wildlife refuge area from which the population had previously been hunted to elimination. By 2015, the population had grown to 180 deer. If this population grows exponentially, find a formula for the function. By defining our input variable to be t years after 2009, the information listed can be written as two input-output pairs. 0, 80, and 6, 180. Notice that by choosing our input variable to be measured as years after the first year value provided, we have effectively given ourselves the initial value for the function, a equals 80. This gives us an equation of the form f of t equals 80b to the t power. Substituting in our second input-output pair allows us to solve for b. 180 equals 80b to the 6th power. B to the 6th power equals 180 divided by 80 equals 9/4. B equals the 6th root of 9 divided by 4 equals 1.1447. This gives us our equation for the population. F of t equals 80 multiplied by 1.1447 to the t power. Recall that since b equals 1 plus r, we can interpret this to mean that the population growth rate is r equals 0.1447, and so the population is growing by about 14.47% each year. In this example, you could also have used 9/4 raised to the 1/6 to evaluate the 6th root if your calculator doesn't have the nth root button. In the previous example, we chose to use the f of x equals a b to the x form of the exponential function rather than the f of x equals a multiplied by 1 plus r to the x form. This choice was entirely arbitrary. Either form would be fine to use. When finding equations, the value for b or r will usually have to be rounded to be written easily. To preserve accuracy, it is important to not overround these values. Typically, you want to be sure to preserve at least 3 significant digits in the growth rate. For example, if your value for b was 1.00317643, you would want to round this no further than to 1.00318. In the previous example, we were able to give ourselves the initial value by clever definition of our input variable. Next, we consider a situation where we can't do this. Example 6. Find a formula for an exponential function passing through the points -2, 6, and 2, 1. Since we don't have the initial value, we will take a general approach that will work for any function form with unknown parameters. We will substitute in both given input-output pairs in the function form f of x equals ab to the x power and solve for the unknown values a and b. Substituting in -2, 6 gives 6 equals ab to the -2 power. Substituting in 2, 1 gives 1 equals ab squared. We now solve these as a system of equations. To do so, we could try a substitution approach, solving one equation for a variable, then substituting that expression into the second equation, solving 6 equals ab to the -2 power for a equals 6 divided by b to the -2 power equals 6b squared. In the second equation, 1 equals ab squared, we substitute the expression above for a. 1 equals 6b squared multiplied by b squared. 1 equals 6b to the 4th power. 1/6 equals b to the 4th power. B equals the 4th root of 1/6, which is approximately 0.6389. Going back to the equation, a equals 6b squared, let us find a. A equals 6b squared equals 6 multiplied by 0.6389 squared equals 2.4492. Putting this together gives the equation f of x equals 2.4492 multiplied by 0.6389 to the x power. Try it now. Given the 2 points 1, 3, and 2, 4.5, find the equation of an exponential function that passes through these 2 points. Example 7. Find an equation for the exponential function graphed. The initial value for the function is not clear in this graph, so we will instead work using 2 clearer points. There are 3 clear points, -1, 1, 1, 2, and 3, 4. As we saw in the last example, 2 points are sufficient to find the equation for a standard exponential, so we will use the latter 2 points. Substituting in 1, 2 gives 2 equals AB to the first power. Substituting in 3, 4 gives 4 equals AB cubed. Solving the first equation for A gives A equals 2 over B. Substituting this expression for A into the second equation, 4 equals AB cubed. B equals plus or minus the square root of 2. Since we restrict ourselves to positive values of B, we will use B equals the square root of 2. We can then go back and find A. A equals 2 divided by B equals 2 divided by the square root of 2 equals square root of 2. This gives us a final equation of f of x equals square root of 2 multiplied by the square root of 2 to the x power. Compound interest. In the bank certificate of deposit CD example earlier in the section, we encountered compound interest. Typically, bank accounts and other savings instruments in which earnings are reinvested, such as mutual funds and retirement accounts, utilize compound interest. The term compounding comes from the behavior that interest is earned not on the original value, but on the accumulated value of the account. In the example from earlier, the interest was compounded monthly, so we took the annual interest rate, usually called the nominal rate or the annual percentage rate, APR, and divided by 12, the number of compounds in a year, to find the monthly interest. The exponent was then measured in months. Generalizing this, we can form a general formula for compound interest. If the APR is written in decimal form as R and there are K compounding periods per year, then the interest per compounding period will be R divided by K. Likewise, if we are interested in the value after T years, then there will be KT compounding periods in that time. Compound interest formula. Compound interest can be calculated using the formula A of T equals A multiplied by 1 plus R divided by K to the KT power, where A of T is the account value, T is measured in years, A is the starting amount of the account, often called the principal, R is the annual percentage rate, APR, also called the nominal rate. K is the number of compounding periods in 1 year. Example 8. If you invest $3,000 in an investment account paying 3% interest compounded quarterly, how much will the account be worth in 10 years? Since we are starting with $3,000, A equals 3,000. Our interest rate is 3%, so R equals 0.03. Since we are compounding quarterly, we are compounding 4 times per year, so K equals 4. We want to know the value of the account in 10 years, so we are looking for A of 10, the value when T equals 10. A of 10 equals 3,000 multiplied by 1 plus 0.03 divided by 4 to the 4 multiplied by 10 power equals $4,045.05. The account will be worth $4,045.05 in 10 years. Example 9. A 529 plan is a college savings plan in which a relative can invest money to pay for a child's later college tuition, and the account grows tax-free. If Lily wants to set up a 529 account for her new granddaughter, wants the account to grow to $40,000 over 18 years, and she believes the account will earn 6% compounded semi-annually twice a year, how much will Lily need to invest in the account now? Since the account is earning 6%, R equals 0.06. Since interest is compounded twice a year, k equals 2. In this problem, we don't know how much we are starting with, so we will be solving for a. The initial amount needed. We do know we want the end amount to be $40,000, so we will be looking for the value of a, so that a of 18 equals 40,000. 40,000 equals a of 18 equals a multiplied by 1 plus 0.06 divided by 2 to the 2 multiplied by 18 power. A equals 40,000 divided by 2.8983, which is approximately $13,801. Billy would need to invest $13,801 to have $40,000 in 18 years. Because of compounding throughout the year, with compound interest, the actual increase in a year is more than the annual percentage rate. If $1,000 were invested at 10%, the table below shows the value after 1 year at different compounding frequencies. If we were to compute the actual percentage increase for the daily compounding, there was an increase of $105.16 from an original amount of $1,000 for a percentage increase of 105.16 divided by 1,000 equals 0.10516 equals 10.516% increase. This quantity is called the annual percentage yield, APY. Notice that given any starting amount, the amount after 1 year would be a of 1 equals a multiplied by 1 plus r divided by k to the k power. To find the total change, we would subtract the original amount, then to find the percentage change, we would divide that by the original amount. A multiplied by 1 plus r divided by k to the k power minus a, all divided by a, equals 1 plus r over k to the k power minus 1. Annual percent yield. The annual percentage yield is the actual percent a quantity increases in 1 year. It can be calculated as APY equals 1 plus r over k to the k power minus 1. This is equivalent to finding the value of $1 after 1 year and subtracting the original dollar.